The year is 1978.
50 years earlier, Einstein and Bose had predicted an extraordinary state of matter, the Bose-Einstein Condensate. But by 1978, no one had managed to produce it. Scientists had tried everything and failed. A quiet resignation was settling in across the physics community, the growing belief that perhaps this exotic state of matter would never be observed, that it was simply unreachable.
But there's always someone, isn't there? Right at the moment when all hope seems lost, someone lights the fuse. A spark of possibility appears out of nowhere. And suddenly, all those years of failure and frustration, forgotten. Everyone gets back to work.
The year is 1978, and two physicists, Daniel Kleppner and his colleague Tom Graytak, were about to set out on a mission to finally end the drought. Kleppner and Graytak decided that the best candidate for the job was hydrogen. First of all, hydrogen was light, the lightest atom there is. And that meant, compared to heavier atoms, it had the potential to condense without needing to get quite as desperately close to absolute zero. On top of that, hydrogen atoms barely interacted with each other. Every sign pointed to hydrogen being the perfect candidate to produce a Bose-Einstein condensate. But cooling these atoms down, that required something far more complicated. Like all atoms, hydrogen has magnetic poles, tiny magnets in their own right. Using this magnetic property, Kleppner designed what he called a cold trap, a chamber surrounded by powerful magnetic fields that could hold hydrogen atoms suspended in place.
But we're talking about an incredibly delicate balance here. Atoms being atoms, sometimes two of them would randomly collide and release energy. And energy means heat, which meant all that painstaking work gone. Back to square one.
But Kleppner and Graytak were far from alone in this quest. Over in Colorado, two physicists who had trained at MIT were about to join the challenge with an entirely different approach.
Cornell and Carl Wieman. Remember those names.
Unlike their rivals, Cornell and Wieman weren't going to work with light atoms. Instead, they turned to the periodic table and chose something unexpected, heavier metallic atoms like rubidium and cesium. Thoughtfully, cooling these heavier atoms would require a completely different approach.
You see, the prevailing wisdom at the time was simple. The lighter the atom, the better your chances. It was a perfectly reasonable assumption, and for the most part, it was right.
But Wieman later said that after years of the easy path leading nowhere, they decided, in his own words, to take the hard road, purely out of curiosity.
And the method they would use to cool those heavy atoms, it was just as unconventional. Laser beams.
Yes, lasers. Now, when most people think of lasers, they think of heat, cutting, burning, destruction.
But that's exactly what the scientific mindset does. It looks at something everyone assumes they understand, changes just one small detail, and suddenly entirely new doors swing open.
Cornell and Wieman discovered that when a laser beam was tuned to the exact frequency of atoms moving at a specific speed, it could actually slow them down. And slowing atoms down means cooling them. Remember, heat is just atomic motion. The faster atoms move, the more energy they carry, and the hotter things get. So when photons, particles of light, slam into atoms inside a gas cloud, those atoms slow down. And as they slow down, they cool. By finding this unconventional solution, Cornell and Wieman had, without fully realizing it, discovered a way to cool atoms to within a few millionths of a degree above absolute zero.
This brilliantly clever solution sent shockwaves through the physics community. Suddenly,
every eye in the field was on laser cooling.
Meanwhile, 20 years had passed since the struggle began in the 70s. It was now the early 1990s. And at this point, a new competitor entered the race, a young physicist in his 30s who had just arrived at MIT, Wolfgang Ketterle. With new configurations of laser beams, the work on cooling atoms was slowly but surely starting to bear fruit.
The excitement was through the roof. MIT threw everything it had behind the research. For the first time in 70 years, there was genuine hope that a Bose-Einstein condensate could actually be created.
And it wasn't just MIT. Laboratories around the world were working at full capacity, each one desperate to be the first team to pull it off.
Remember the race to liquefy helium? The rivalry between Onus and Dewar? A similar energy was sweeping through the scientific world. That's why in a field like this, you have to move fast. As Eric Cornell himself put it, life was short, time was limited, and science kept marching forward.
So Cornell and Wieman got to work in their Boulder, Colorado laboratory. They combined every technique they could get their hands on, building a chamber to trap the gas, installing advanced laser systems to slow the atoms, and layering in magnetic field traps on top of everything. On the other side of the country, Ketterle had begun his own work at MIT, using similar approaches, but with sodium vapor instead.
Cornell and Wieman in Boulder, Ketterle at MIT. As all of them would later describe it, it was a friendly rivalry. In fact, they would sometimes share hints with each other, trading findings back and forth.
But when it came to crossing the finish line, everyone wanted to get there first.
But at a certain point, laser cooling and magnetic trapping alone wouldn't be enough. They would need one more technique, evaporative cooling. And the logic behind it is actually beautifully simple. Think about a hot cup of coffee and the steam rising from it. That steam? Those are the hottest molecules escaping from your coffee. And as they flee, they take their energy with them, which is exactly why your coffee cools down. They applied this exact same logic to atoms. Gather them inside a magnetic bowl, a trap shaped like a basin. The highest energy atoms escape over the rim, taking their heat with them. And as the trap's walls tighten, what's left behind gets colder and colder until the atomic soup is ice cold. By gradually tightening the trap, squeezing the boundaries closer and closer, they were inching toward the conditions needed to produce a Bose-Einstein condensate.
Cornell and Ketterle were getting talks at conferences around the world. Everyone was asking the same question, how close are you? And both teams were watching each other's progress like hawks.
They were now in the final stretch of the race. And then, on June 5th, 1995, the day finally arrived. One of the most important days in the history of physics. The team at the Boulder Laboratory, led by Cornell and Wieman, had done it. They had successfully created the Bose-Einstein Condensate, the state of matter that Einstein had theorized 70 years earlier. Of course, their first reaction was, wait, is this real? They had to be absolutely sure.
Because this condensate, this new state of matter, was like a vampire. Even the tiniest amount of light could destroy it completely. It was a substance that could only exist in total darkness.
But here's the clever part. You could still photograph it. By firing a laser beam at incredible speed, even though the condensate would be destroyed in the process, its image would be captured on film, a ghost print of something that existed for just an instant. After running every possible verification, Cornell and Wieman confirmed what they could barely believe. They had produced a pure Bose-Einstein condensate from about 3,000 rubidium atoms, cooled to 170 billionths of a degree above absolute zero.
In the entire universe, as far as we know, this was the very first time matter had ever taken this form. A historic moment.
Just weeks after this triumph, Wolfgang Ketterle at MIT achieved something equally remarkable. Using sodium atoms instead of rubidium, he cooled roughly 500,000 atoms to a near standstill, producing even more condensate than Cornell and Wieman had. So much, in fact, that it was visible to the naked eye.
And when it came time for recognition, all three scientists, rivals who had pushed each other to greatness in different laboratories at different times, were honored as they deserved. In 2001, Eric Cornell, Carl Wieman, and Wolfgang Ketterle shared the Nobel Prize in Physics. Now, if you're wondering what happened to Daniel Kleppner, the man who started this entire race in the first place,
In science, there's no room for bitterness. Even though others had already produced the condensate, Kleppner didn't take a single day off. He kept working.
and after 20 years of relentless work, in 1998, Kleppner finally produced a Bose-Einstein condensate using hydrogen.
He may not have won the Nobel Prize, but when he stepped onto the stage at the Enrico Fermi International School of Physics, where the greatest physicists in the world gather every year, the entire audience rose to their feet, and they applauded him for minutes.
What truly mattered was this: he had earned the respect of his fellow scientists. At this point, you might think the race is over. Time to hang up the lab coat and retire.
But remember what we said. Every new discovery, every great breakthrough is really just the beginning of countless new questions.
And I think there's a question that's been sitting in the back of your mind this entire time. Okay, we theorized this new state of matter, we fought for 70 years, and we finally produced it. Great, but now what? What are we actually going to do with it? What's the practical point?
And yes, it will be useful. Incredibly useful, in fact. But that's a story for another time. And that's exactly why I always say, everything has a story. And you can't truly understand something without learning the story behind it.
Everything, even a person. You can't claim to truly know someone without understanding the background that made them who they are. The same goes for a formula, a scientific idea. What was the motivation that gave birth to it? Who were the people, and how did they think to bring these incredible ideas into existence? And that is exactly what I'm trying to do with Science Mosaic, to pull back the curtain just a little and take what we've learned beyond mere knowledge to truly understand by telling a story.
And that's why I'm going to keep telling the story of science for a very long time.
And if you'd like to support me on this journey, you can contribute through the subscribe button.
A huge thank you to everyone who has contributed so far and continues to support this journey.
And as always, until we meet again, I'm glad you're here. With love.